Hi. Today we're going to take a look at applying half reactions and and redox reactions in probably the biggest engineering approach that you're going to see in a Regents chemistry course. I might need to correct that later, but at least that's how it feels to me right now. We're going to take a look at voltaic cells, which if you're unfamiliar, we're going to obviously talk about it today, so let's get started. So quick as a do now reminder, this is not of what we did last time. We're actually going to go way back a couple of months ago. Take a look at these single replacement reactions and determine if they actually happen. If they actually happen, I want you to hit the pause button. I want you to predict the products. You might need to balance the reaction, but go ahead and take a few minutes and do that. This is going to be good. This reminds us of where we were. Excellent. So, taking a look at the first one, from what I remember, more active metals need to end up in compounds. That's the way that the activity series works, and the activity series governs how single replacement reactions work. So taking a look, here we've got the metal lithium, and so the replacement would be between the metal lithium and the metal silver. We see silver is way down here, lithium is way up here, so this reaction is going to happen. Lithium will make a +1 ion, so that'll be a 1-to-1 ratio with nitrate, and then you'd get silver metal. For the second one, let's say we've got sodium and magnesium. They're right next to each other, but sodium is more active, which means we're going to make sodium sulfate, but keep in mind that sulfate's a -2 ion and sodium only makes a +1 ion, so that's going to be your neutral formula. We're going to make metallic magnesium, and then we kind of have to balance this out a little bit, but we're balanced. And then for this third one, here's copper and here's iron. Iron is the more active metal, so the more active metal is already in a compound. There is no driving force in terms of chemistry for this reaction to take place, so no reaction. Now, just as a slight, we're going to get well into this more in a couple slides, but just as a slight preview, something to think about with this is now that we've spent so much time talking about redox reactions, oxidation, and reduction, we can look at these single replacement reactions through that lens, and now I think we can get a better picture of what table J actually stands for in terms of why things are the way they are. We've talked before about why is table J built the way it is? Why is it that cesium is actually less active than lithium? That doesn't make any sense. It does once we actually consider a couple more things. But before that, I don't want to lose track of what we're talking about. I'm going to play 2 videos for you, and don't get me wrong, I like Hank Green a lot. But he says something that's wrong in this video. Now, I'm not going to play the whole of both videos because I think the big error that they have is at the beginning of the video, so we'll pause it. I'll put links to both the videos, but I want to put some ideas in your head. I want you to watch, take some notes, see if you have any questions, but apparently we're talking about lemons today.
Hello and welcome to SciShow Experiments. Today, we're discussing what may be the most cliche and well-known science experiment of all time, though it is also one of the most misunderstood science experiments of all time. The important thing to note here, the electricity is not in the lemon. First, let's do this thing. Now roll the lemon around a bit to break up all the little juice packets inside to get it nice and juicy. Stick a nail in one side. It has to be a galvanized nail, meaning it's coated in zinc. And on the other side, stick something copper. I'm using copper wire. You'll probably be unsurprised to discover that when I connect this voltmeter to the copper and the zinc, it will show some electric current. But if I asked you why there are electrons flowing from one metal to the other, there's a fairly good chance that you would either be stumped or you would be wrong. So let's fix that. Electrochemical cells, also called batteries, require 3 things: 2 electrodes and 1 electrolyte. One of the electrodes has to have a stronger desire for electrons than the other. In chemistry, we say that it has a higher electronegativity. That electrode, the one that wants the electrons more, is called the cathode, and the one that gives up electrons is called the anode. In our lemon battery here, we have copper in the wire and zinc from this galvanized nail. Copper likes having electrons more than zinc, so it's more electronegative and thus our cathode. But if that's the case, then why can't we just hook the copper to the zinc and watch the electrons zoom across? And what's the point of the lemon? I bought a lemon and I want to use it. Well, electrons aren't just going to abandon their nice stable home and make the metal all positively charged on one side and negative on the other. There are a ton of forces that prevent that from happening. Since zinc is losing all those electrons, it's going to have to lose protons.
Well, he's getting like way ahead of himself. And don't worry, like I said, I'll play the whole video, but he's getting a little bit too far into it. And I didn't want to play the whole video anyway because, well, that's the lesson. But these guys seem to like lemons too, so let's take a look. I'm not paying the whole 12 minutes.
Electricity to support this beast. It's Volkswagen's carbon fiber dual engine, faster than a Formula One electric supercar, for the upcoming infamous 12.5-mile Pikes Peak race to the top of a really high mountain in Colorado. And they gave me no further instructions on how they wanted it done. So I thought, how cool would it be to charge it up using one of those science fair lemon batteries? And since I'm pretty sure using only one lemon isn't going to cut it, my plan is to build the Guinness World Record world's largest lemon battery. And when it comes to making ridiculous things, no one is better at that than fellow YouTube engineer, William P. Osmond.
Oh.
The first video I saw of yours was when you biohacked your dog. How did that work?
Not well. We tried to dangle a hot dog in front of a dog's face on a mechanical backpack, and then you can steer the hot dog to try to get the dog to change directions, and what he ended up doing was sitting down and eating them.
So we estimated this should take about 3 days for us to build, and yet I've only allotted 2 minutes for this in the video. So you know what that means.
Do you plan on your videos working?
We didn't want our battery setup to just be a mangled mess of wires, so William had the brilliant idea to water jet out a bunch of copper and zinc strips, which we could then assemble into racks. We wired the first half of the racks to be in parallel, and that was in series with the second half of the racks, which were also all in parallel. And then at that point, all we had to do was impale some lemons. Speaking of which, in addition to harvesting from my own backyard, I visited some local farms and got their Class 2 lemons, which means they couldn't be sold in stores because they were either overripe, misshapen, or too small. And when one finds oneself in possession of 1,232 lemons, turns out you can't not do this.
I think I need to buy a trampoline.
What's my safe word? So here we have the world's largest lemon battery, and now is the moment of truth to see just how much power this could actually make for us. But in order to understand the results, let's first review how a lemon can even make power in the first place. The trick is picking the right metals to stick into the lemon. In this case, zinc really wants to get rid of electrons, and then copper really wants to collect them. But they can't do that unless they're connected by some kind of electrolyte, and that's the lemon juice. Once that happens, an electrochemical reaction occurs at the base, and the electrons can now move. And moving electrons is the very definition of electricity. It's sort of like how the water up high in the full cup naturally wants to flow to the empty cup lower down, but it can't do that until you connect the two with the straw, which allows the water to flow. So in this case, obviously, the higher cup is the zinc, the lower cup is the copper, and the straw is the lemon. And so then the flowing water represents our electricity or power. And so with that, we're measuring...
So he goes into it, and there's obviously 10 more minutes of video. I don't really want to get into it, but again, the same idea where this zinc and this copper comes in. There are a lot of words thrown out there. There's voltage, there's current. So I want to dig into this a bit before we revisit these videos, because I feel like maybe we're not going to be in the best place to understand it unless we actually talk first. But it does seem to be that the word battery is bandied about a lot, and then we're using this battery to power something. So talking about how a light bulb works, talking about how a battery works, probably a good idea for today. Really quick, the light bulb is the easier of the two. This is one of your old incandescent lamps. This is some tungsten wire, and as the tungsten wire heats up, it starts to glow. That's what the light is. There's some light on my face right now. I got a lamp pointed at me. Right now, there's energy being dumped on this. This is actually a CFL, but it works in a similar fashion, just not quite the same way. where the electricity goes through, the electricity dumps energy onto something, and that results in light. In this case, we're increasing the temperature. The CFL, it's excitation emission. But as the wire heats up, it glows. And that heat comes from the electricity from being plugged into the wall or coming off of a battery. So these batteries seem to create energy somehow. But I figured if we want to understand how a battery works, there's a couple things we need to talk about. First, here's a cross section. If we're going to have flowing electricity, it sounds to me like we have flowing electrons, or in other words, if we want to relate it to a chemical reaction, electrons being lost and gained. So really what we're trying to target is a redox reaction. So, and in the simplest way I can put it, a battery is a controlled redox reaction where the electrons can be transferred from one substance to another, but we've built it in such a way that they have to go through a wire. So in this is your cross-section of a battery, and actually the casing is made out of zinc, it says right here. And then you can see that it's connected to the negative terminal on the bottom, and we'll talk about this, but electrons flow out of the negative, which kind of makes sense, right? Away from the negative. And then the positive terminal up here with this cap is connected to this carbon rod. Now, I know carbon's not a metal, but we saw before in all our previous reactions, nonmetals can participate in redox reactions too. But you can also more specifically see that there's complete separation between the zinc metal and the carbon rod. So there's no way for the electrons to go through because they're not touching. And I wanted to make a video, I'll make one eventually. I have some silver coins that have tarnished, and you can actually use direct contact chemistry, redox, to fix the tarnish. I'm not talking about polish. Polish is the enemy here. I'll get into that in my video, but it's this separation here that means that when you put the battery in whatever device you're trying to power, that the electrons will go out of the negative terminal through all the wires and come back into the positive terminal. Couple things to mention. Voltage was a word that was thrown out a bit. Voltage is a measure of energy per unit of charge. In this case, since we're talking about electricity and electrons, it's the amount of energy carried by each electron. We've talked about a number of things like ionization energy and electronegativity, and voltage is another way to measure energy and electrons. In a way of putting it, when atoms lose electrons, atoms loses. When atoms lose electrons, the electrons gain energy. When atoms gain electrons, the electrons lose energy. So like if the electron's going to fly off, it has to absorb energy to do so, and when it falls into your other atom, energy is released. Well, the amount of energy released per electron, that's voltage. And so you can imagine that different metals, it requires a different amount of energy to remove an electron from each metal. We talked about ionization energy, and it's kind of related to that, but we're just kind of looking at it a different way because we're taking that ionization energy and we're dividing by the charge of the electron. That's all I want to say about that. The word current was said too, and current is a measure of the flow of charge. So it's like how many electrons per second is a way of thinking about it. So I'll write that. It's charge over time. So like electrons per second, or there's other units, it's coulombs when you get into physics. But that's the rough idea. So in this battery, we've got this redox reaction that happens through a wire. To better understand this, I'm going to show you a picture that maybe looks less easy to understand. Sorry. What's his name? Galvani and Volta, Alessandro Volta, and I can't remember the guy's first name, Galvani. There were a number of scientists around the Enlightenment who started realizing that certain metals, because the technology was getting in place to purify metals, that certain metals, you could start to see this thing called electricity flow by putting things together in certain ways and measuring it just the right way, and that's where the really first primitive batteries came from. But every battery, as Hank Green said, is an electrochemical cell. So it's any conversion between electricity and chemistry. And when I say chemistry, I mean literally changing a substance, like gaining and losing electrons. Just to put a couple words to it, there's two different kinds of electrochemical cells. There's electrochemical cells that take chemical reactions and create electricity from it. Those are your batteries. And then there's the opposite, where they will convert electricity into chemistry. So a voltaic cell and an electrolytic cell are opposites in terms of the science that they accomplish. And then one more word, I think both videos mention it, electrodes are being used. An electrode is anything that carries electrons to and from a substance other than a metal. Other than a metal? Why did I write that? The electrodes in this point, so the point is the electrode connects the battery, which the battery actually is, and this is why it's confusing, this is basically the battery. So this piece of metal connects the light bulb to the battery, and then this piece of metal connects the light bulb to the battery. If we go back to our picture, if we go back to our picture of the battery, you'll notice that the actual negative terminal is a piece of metal that's not the zinc. And the positive terminal is a piece of metal that's not the carbon. And so these pieces of metal connect the two metals that are involved in the reaction. And that's why we call those electrodes, positive and negative electrodes. So to understand what's going on here, I have to give you a little bit more information, but there's a lot of like labels here, and I'm already getting a little bit messy. Let me clear up everything, and I'll give you a little bit more information. This bar is made out of zinc, and this bar is made out of copper. Same examples in the videos. This solution is zinc sulfate, and this solution is copper sulfate, copper 2 sulfate. I believe there's some potassium sulfate in this tube here. Aqueous, of course, and aqueous, and aqueous. And I actually think that's enough labels, but we're going to take a look at the beaker on your left. First, because, I don't know, I like starting going from left to right, but we want to take a look at the chemistry that's going on here. Now, if we were to take a look at this, I'll tell you this and then we'll kind of double back to talk about it in a second. The reaction that's happening, based on all the labels that are drawn here, the reaction that's happening, it seems to be that electrons are being sent that way, away from the metal, away from the zinc. If we are losing electrons, we are oxidizing. Now taking a look at this, we're actually going to zoom in this picture here on the far left, and what happens is, in this half reaction here, the zinc solid is becoming zinc aqueous. And the reason that works, don't forget, is that the zinc solid, the elemental neutral zinc, is held together by metallic bonding. Metallic bonding is that sharing of that network of loosely held electrons. They're all kind of loosely held. And so in this oxidation, those loosely held electrons are being sent away. And if you send away those loose electrons, the metallic bonding fails. Because all of these atoms, all of these ions, these positive ions in the sea of electrons, they're all held together by that sea of electrons. If you start sending the sea away, there's nothing holding together, and even worse, it's a bunch of zinc positives all hanging out near each other. They're going to repel each other. So what ends up happening is literally this region had a bunch of atoms in it, and then as those atoms lose electrons and become ions, they leave the metal. So if you let this electrochemical cell, this voltaic cell, run long enough, you're actually going to start to notice like chunks of zinc starting to disappear, and the zinc bar is going to shrink and shrink and shrink until eventually there's no zinc left, and actually like shrinks. And what would happen is you're not like destroying matter. What's happening is the zinc atoms become zinc ions in solution. And so if you are decreasing the amount of solid and increasing the concentration of the ions, that would mean that the mass of the bar, which is just the solid, decreases. The last thing I want to say is this zinc bar, this electrode, it has a specific name because it is the site of oxidation. It gets called the anode. So I'm just going to write a little mnemonic device here. Anox, that's how I remember it. You'll see the other half of it in a second, but just picture an ox. So like I said, I want to double back and talk about this. In this reaction, I totally changed the size of the beakers, and then I did not change the path that the electrons take, so they're kind of flying a little too far to the right. My mistake. But what we said was the electrons are flowing out of the zinc, and both the videos said the same thing. They're going from the zinc to the copper. Why? Now, if we were to actually write the overall reaction for what's happening, zinc metal, if we were to just mix everything together, the zinc metal would actually not react with copper metal, it would react with copper sulfate to make zinc sulfate and copper. Now, going back to our do now, this is a single replacement reaction, and as you can see, zinc and copper are here and here. And we notice that the reason this happens is that zinc is more active than copper. But notice that we just hooked everything up. We didn't like set up any roadways or draw any arrows. Like, we're not forcing electrons to do anything. Electrons are just doing what electrons do. And so why do the electrons do what the electrons do is really the question. And it's the activity series that tells us. If we were to pull this apart really quick, our oxidation half reaction would be zinc becomes zinc ion plus 2 electrons, as I said in the previous slide. And then the reduction would be that copper ions would gain 2 electrons, which we'll see on the next slide, and become copper metal. So we can kind of connect these two, table J and the half reactions that we have. Really, metal activity means likely to be oxidized. When it's an atom. And then low activity means likely to be reduced as ion. So I'm not saying that copper metal is likely to be reduced to copper negative ion. What I'm saying is a more active metal means that the metal is more likely to oxidize and become an ion. And a low activity metal means that its metal ion is likely to be reduced to become a metal. Everything I just said is absolutely reversed for the nonmetals. Fluorine is likely to be reduced as an atom, and iodine is more likely to be oxidized as an ion, although that said it's not really terribly likely to be oxidized. There is a way to mush all of these together. If you start looking at the, voltage of the half reactions, you can actually put the nonmetals and metals all together into one big long activity series. And I can put a link to that. I mean, that one, you can trust Wikipedia for that. And it shows everything that on the same table. But yeah, that's kind of why I had you guys look at single replacement reactions at the do now. Single replacement reactions are governed by the activity series, and the activity series is governed by the voltage of oxidation and reduction. And so it all kind of ties together. In this case, electrons are always going to flow from the more active metal to the less active metal, always. So I'm not saying left to right in every case, I mean, just happened to work out this way, but there are plenty of incidences where the electrons will flow from right to left because all I gotta do is switch the beakers and switch the metals. So like it's circled here, I wanna take a look. We've already got a label here to talk about, and we've got some charges. So actually before I move on, sorry, the one thing I will talk about are these charges. Remember on the battery, we have a negative and a positive terminal, and that's the same thing here. Just like with a battery, we actually need to use table J because, I mean, obviously when you buy a battery from the store, it's already built a certain way, so like the people who made the battery know how it's going to work, but you're looking at batteries. The way we define the charge of the terminals is by the electron flow. So that's probably the last thing I'll say here. the electrons are going to flow from the negative terminal to the positive terminal. You can think of electrons like they're negatively charged, so they're going to go away from a negative and towards a positive, but that's how we're going to define this in every case. So once you use table J, like once you have a reaction, you look at table J, or if you have table J, you look at a reaction, other way around. As soon as you figure out which way the electrons are flowing, you now know what the charge of the electrodes are. The anode in this, for these voltaic cells, is always going to be negative, and the cathode, which is where this reduction occurs, is always going to be positive. So if we look right here, this is our reaction that's going on, and this is our half reaction. So we see reduction. The copper ions are becoming copper metal. I'll put the 2 electrons in. All right, gain electrons. So in stark contrast to the zinc electrode, the copper electrode here, what's happening is the electrons are coming over from the zinc, and they're meeting up with copper ions that are in solution. They're actually migrating over to the metal and meeting up with those electrons that just got sent over, and they're becoming copper metal. So instead of removing the metallic bonding, we're creating larger sea of electrons. So more copper solid atoms, which means it gains mass. So if you were to watch this solution for a while, this copper bar would just get bigger and bigger and bigger and bigger. As you might guess, the solution is going to get less and less blue because copper ions are becoming copper atoms. And there's one thing I want to say before I forget, because I forgot on the last one. The electrons that are lost and gained have no mass, right? We learned that electrons have negligible mass. The change in mass of these metal bars is not due to the gain and loss of electrons directly. When zinc loses electrons and the atoms fall off as ions, zinc has what, 27 protons, 27, 28 neutrons. That's a lot heavier than 2 electrons. It's the loss of the particle, the atom and the ion. That's what causes the change in mass. The change in mass here, the electrons coming over, not going to add any mass to the bar. When the copper ions attach and become metal, though, that's gaining, I don't know, 60,000 times more mass than the electrons. It's the gain and loss of the particles, not the electrons, that cause the change in mass. And then again, we're gonna relate the word reduction to cathode. You do remember cathode ray tube from the beginning of the year? It's the same cathode. But the mnemonic device, there's a couple. You can just picture a red cat. You can picture an ox, and that might help. I noticed that an ox, 2 letters each, and red cat, 3 letters each. An ox is grammatically correct. An cat would not make sense. An red does not make sense. There's a number of ways to get around it. Whatever works for you, but this is the real device in terms of giving names to things. So you need to be able to identify half reactions, use table J, and go through that whole process. This is rather lengthy. There's one more thing. There's like 4 more things, I'm sorry. But there's one more component we haven't talked about, the salt bridge. So I think there's nothing on, there's nothing on this slide. Oh, well, I'll skip the next slide. I'd said before that this is filled with potassium ions and sulfate ions, and that serves a purpose. If this reaction were allowed to run without the salt bridge, the electrons would be leaving the zinc and they go to the copper. Even if the electrons were just allowed to run crazy like that, what would happen is the amount of zinc ion would go up, and the amount of copper ion, the concentration, would go down. But remember that I said zinc sulfate and copper sulfate were present in the solution, which means there's still the same amount of sulfate. There's no change in the sulfate in either case. This means that if you have more zinc ions and the same amount of coppers, this solution would slowly start to build up a positive charge, and this solution would slowly start to build up a negative charge. And this is bad, because if the electrons are supposed to be flowing this way, that buildup of charge is actually counterproductive to the flow of electrons. We said that the copper electrode should be positively charged, if anything. And if you got to build up a negative charge in the solution, it's actually going to push back on the electrons. In fact, if you were to remove that salt bridge between the two beakers, you would see that the light bulb would turn off almost instantly. That buildup is super quick. So what really this salt bridge does is the salt bridge conserves ionic neutrality. So you don't want the reaction to stop, and obviously it doesn't stop because batteries still work. So what's going to happen is, with this buildup of negative, is we should see some of these positive ions that we put in solution start to migrate down in there to keep it neutral, to allow more electrons to flow. And we're going to see these sulfate ions move over this way to counterbalance all the new zincs that are coming into solution. You want to keep your solutions electrically neutral. Even though the total ion concentration is changing, it is doing so at an even anion to cation ratio. By setting this up in such a way where there's two beakers, we've created what we call half cells. Get it? Because each one's like, half. And even better, a half cell is the site of a half reaction. In a way, we've made it so that all the zincs are by themselves, and that's just the oxidation. So we've actually physically separated a redox reaction. We made it happen in two locations. But the half cell houses the half of the reaction, basically. And then the way I actually help remember this is, once we've correctly labeled the anode and the cathode, super easy. Anions flow to anode. Cations flow to cathode. There's obviously, like I said, go back a minute or two, and there's a full explanation as to why, but I like giving that as there's the information. But yeah, that's the way in which it maintains that electrical neutrality. That sulfate is getting really, really tiresome, isn't it? Next slide. So a word about this. Remember that if we mixed everything together, the reaction would still happen. The issue is, you wouldn't get as bright a light, if any light at all. Since the overall redox reaction is between these two species, the only things that are necessary are the zinc and the copper sulfate. It's actually not necessary to have zinc ions in your solution. It's actually not necessary to have a copper bar. In fact, if I could go way back and take a look at this picture, if this bar wasn't made of copper, as long as it was electrically conductive, the reaction would still run, because the thing that's being reduced isn't the copper bar, it's the copper ions. And interestingly, if you stick in something that isn't copper and you let it sit for a while, and then you take it out, it would have a layer of copper on it. You actually would create a layer of copper metal from the copper ions on your substance. As long as it was electrically conductive, it would work great wherever the solution made contact with the electrode. So sometimes you'll see, instead of copper, you might see something like a carbon rod, because you don't want to get metal contaminants, and graphite is electrically conductive. Which is why in the other battery you saw that carbon rod at the positive terminal. Remember that the positive terminal is the cathode, that's where the reduction occurs, right? So you're seeing a little bit of the engineering come into play here. The zinc ions, not super necessary down there. You do need some ions because you need conductivity. And we learned a long time ago that electrical conductivity comes from mobile ions. But you don't need to put zinc solution in that beaker. You can put any solution you want as long as there are ions. That said, you want to be careful because if you put something down there that reacts with the zinc metal, you're going to short circuit your battery, and if there's a reaction happening in this half cell, there's going to be no reason for electrons to go through there. I mean, entropy being what it is, there will be some, but what I'm saying is, obviously, this here is like your gold star way to set it up. You want to put zinc metal in zinc solution and copper metal in copper solution because it limits that side reaction possibility. But it's not really necessary, and that's how you can get away with things if you're trying to do some of this at home. And that's also where you get away with things when you start setting up like things like lemons. But before we get back to the lemons, now we're down to two more things. Let's talk about what happens when a battery dies. So if this reaction keeps running and running, like I said, and this bar keeps shrinking and shrinking, and this bar keeps growing and growing, eventually the zinc metal is going to run out. And if there's no zinc metal, then you can't have any reaction. Eventually, the concentration of the copper ion would go to zero, and the solution wouldn't be blue anymore. It would be colorless because of all the other ions that are present. Or maybe you'd run out of ions. Now, the one thing I'd say there that last one's very unlikely because what's going to happen is you're going to get more diffusion. Like there's going to be some ions working their way up into the solution, and maybe like there's all sorts of ions going in all directions. Basically, it becomes a big mess. But the big mess, don't forget, big mess is entropy. And if the entropy of the universe is always increasing, batteries die when the reaction is over and you've reached maximum entropy for that system. Hold on a second though. If this runs on a battery, and that's how a battery works, then, I mean, this phone has been working for 2 years. Knock on wood, right, for now. But when you get a new phone, you don't get it because the battery has stopped working. You can recharge batteries. I mean, to think about it, the electrons based on table J are going to flow this way. And that's what's going to cause the buildup and the depletion that you see. If we could somehow remove the light bulb and, I don't know, add a plug where we like charge it from like the wall, we could force the electrons to go this way. And then what would happen is, if we force the electrons for long enough, the bars would actually rebuild and deplete back to where they started. And then as soon as you unplugged it from the wall and hooked up the light bulb again, it lights back up. And then you can keep going back and forth and back. Now the thing is, when you plug into the wall, you're using electricity, so you never really get free energy because you're using the electricity that's being made available to you. But you can actually recharge a battery by applying energy from some other source. Okay, almost done, almost done. So as a brief summary, I want you can hit the pause button, you can go back in this video. Here's another reaction between lead and silver. And I want you to try and do a full workup of this. This is another Voltaic cell, and I want to see if you can figure out everything. I'm going to jump right into it, but please hit the pause button if you want to figure it out yourself. I encourage you to do so. I just know this is a long enough video already. So the anode in this case is going to be lead, the cathode is going to be silver, so we're going from lead to silver. The salt bridge is here, found it. The half reactions, so we're going to be turning lead into lead 2 because that's what it says right here, plus 2 electrons, and the silver is going to gain an electron and become silver metal. And of course, this is unbalanced. That means you can go back and balance it if you needed to. The anode, which is lead, will decrease, and the cathode, which is silver, would increase. And that's basically it. In this case, it does turn out that the electrons again flow from left to right. That's not always the case. That's not always the case. So that's about it for me, except we actually haven't figured out the problem. I'm not going to spend your time by playing the videos again, but I'm going to link both of these videos below. Watch the first few minutes again. In the parts that I played at the beginning of this video, both people said something or showed something that was factually incorrect. If you figure out what it is, post it in a comment below, post it on Classroom, post it on Discord. I want to hear what you guys think is incorrect about these videos. Thanks for watching.